Let's look at another type of neutralization reaction where we're looking at a weak acid with a strong base or a weak base with a strong acid. So I'll do the first scenario for you where we look at something like acetic acid reacting with a strong base. Let's use lithium hydroxide. And that's any of our group 1 and 2 metal salts, with the exception of beryllium and magnesium, remember. Okay, and if this is going to occur, we'd have a swap of my hydrogen from the acid and then my metal. So we'd end up with lithium acetate and water. And water is a pure liquid, and this would be aqueous. Okay, now let's check and make sure it's balanced. We have 1 lithium, we have 1 acetate, we have 2 protons, and 1 oxygen. So we're good. We've got our weak acid, strong base combination here. What's our driving force? Do we form a solid precipitate? No, this salt is soluble. Water is a liquid. So of course it's not going to be considered. And then there are none of them are gases, and so we would think, okay, well, water is a non-electrolyte. So that is going to be my driving force here for the weak acid, strong base, and as well as the weak base, strong acid reactions. So we can break this into our complete ionic equation as we've done before. And the complete ionic equation is going to, remember, dissociate my soluble strong electrolytes. So is acetic acid a soluble compound? Yes. Is it a strong electrolyte? No. Okay. We know that it is an acid, and it's not one of those 7 strong acids, and any other acid would be considered weak, and it is not a strong electrolyte. So we would not dissociate this. Okay, so CH3COOH will stay as 1 unit. We will dissociate the lithium hydroxide because it is a strong electrolyte. It's one of our strong bases. It's an ionic compound. And then my products, I would have lithium and the acetate, anion, and then water. Okay, so this is my complete ionic equation. The third step is going to be the same as we've seen before, where we eliminate spectators, those ions that appear on both sides. So I have lithium as the only spectator in this particular example. We would remove that to give the net ionic equation. So we have my acid reacting with OH minus. So any hydroxide would result in the same outcome here, no matter what the metal choice was. And there we have it. This is our net ionic equation for the reaction of a weak acid with a strong base. Are you able to give it a try for a scenario involving a weak base and a strong acid? We'll look at the result in a minute. So I just had you look at the example where we're using NaF, which would be considered a weak base. F minus anion is the conjugate acid of a weak acid, HF. And so that would be said to be weak. And then HCl we know is a strong acid. So let's see if a reaction will occur here. We do the swap and we get HF and NaCl. So we'd have to ask ourselves whether or not we have any solids forming, any gases evolving, or we form a weak or non-electrolyte. And so HF is an acid, it's not one of our 7 strong acids, and that's a common thing that gets mistaken as one. So HF does not completely dissociate. We would consider it a weak electrolyte. So it does dissociate to some extent. And NaCl, as you know, is soluble. So we have a weak electrolyte forming here, which would be my driving force. Okay, we have a driving force. Now let's look and reduce this down to the net ionic equation. So we'll dissociate those soluble strong electrolytes and see what we get here. HF, remember, is not a strong electrolyte, so we would leave it as 1 unit. And I went ahead and got ahead of myself here. So sodium plus chloride. All right, and then we would eliminate spectators, those that appear on both sides. So sodium does, and chloride as well. So we end up with a net ionic equation as F minus plus H plus, giving me HF, a weak electrolyte. So if you got that, great. If not, why don't you give a few more practice problems a try and let me know if you have any questions. Thanks for watching.